So now I am sharing my today's presentation slides. Just a minute. All of you see these slides? Just write in the chat box. Okay. So let us start today's class, and these are the last topic of Unit 1. So today we are going to study the remaining three topics of Unit 1. These topics are stacks, queues, and subroutines. So let us start uh, each topic one by one. So as we already discussed stack in our last class. So continuing the last class, uh, we will discuss the stack as all of you know that the stack is holding the property of leaf of property, means last in first out property. So now the stack is also used as a memory. So we are discussing the stack memory here. A stack can exist as a standalone unit, or it can be implemented in a random access memory attached to the CPU. So it can be used as standalone as well as attached with the CPU. The implementation of a stack in the CPU is done by assigning a portion of memory to a stack operation and using the processor register as a stack pointer. So in the next slide we will we will show the stack memory, and in that memory the stack pointer is also there. So figure, you can see the figure shows a portion of computer memory partitioned into three segments. So a memory is partitioned into three segments. In one segment we store the program, in other segment we store the data, and in the third segment we store the stat. And basically here stat is in the form of memory. So the program counter points at the address of the next instruction in the program. So basically, it is the use of program counter to point at the next instruction in the program. Then there is the address register is also there, which points at an array of data. So moving to the next slide. So as you can see from the diagram, that a stack is there. uh, the the whole memory is divided into, this is the memory unit, and the whole memory is divided into three parts. First is the program, second is the data, and the third is the stack. So here you can see the stack can be represented with the stack pointer. The This is the address register, which denotes the data part, and this is the program counter. So they are just pointing the what is the value of the program counter here. It is pointing the value of the address register, and it is pointing the stack pointer value. So on the right hand side of the figure you can see there are addresses. So the memory is in between the 1000 address to 4001 address. So this is the range of the memory. So here you can see that a stack contains the memories from the 3000 to 4001 memory address. So we are discussing this memory address in particular, as we are discussing stacks here. So just remember this figure, because in next slide we are discussing this in much more detail. Here you can see here that 3000 is the starting point of the stack, and and here 4001 is the ending point. So these are the two end points of the stat, 3000 and the 4001. So moving to the next slide, just remember these values. So a stack pointer, which is abbreviated as SP, points to the top of the stack. The the three registers are connected to a common address bus, and either one can provide an address for memory. As you can see that the three registers are, one is the stack pointer, the other is the address register, and then the third is the program counter. So program counter is used during the fetch process to read an instruction. As we already discussed, in there are four phases. The first phase is the fetch phase, and the last phase is the execution phase. So AR, the address register, is used during the execution phase to read an operand. And SP, which is the stack pointer, is used to push or pop items, which are the operations of the stack. There are two operations of stack, which we already discussed in the last class: the push operation and the pop operation. So SP, the program counter, is used to push or pop items into or out of the stack respectively. The initial value of the stack pointer is 4001, as we already uh, discussed in our last slide. In the diagram, the stack is from 3000 to 4001. So basically it starts with the 4001 value, because once we enter the item in the stack, it goes to the bottom. So the initial value of SP is 4001, and the stack grows with decreasing addresses. As we insert more and more items in the stack, then the value will be decremented. Just like the first item is stored in the stack is at address 4000. The second item is stored at address 3099, and the last item that can be used for the stack is 3000. So basically the SP, the stack pointer, which is uh, showing the value of 4001, it basically contains the symbol dollar, which basically denotes the bottom of the stack. And that's why the first item of the stack is stored at the address 4000, and so on. The items can be stored in a decreasing order. So but no provisions are available for a stack to limit its stack, because it is an infinite uh, stack is a linear infinite memory basically. So you can understand this by seeing this figure as well, that the 4001 is the bottom of the stack, and we need to insert a dollar sign here, which denotes the bottom of the stack. And after that, the first element is stored here, then the second element is stored in 3999, and the last element is stored in the 3000 place. If there are more elements need to be inserted in the stack, then we need to pop the already inserted elements in the stack. And after that, we as the element of the as the memory in the stack is empty, after that we can push more elements in the stack. So basically this is the memory stack, and we can use it by using this figure. And basically here the stack pointer has major role. So all of you understand it, just write in the chat box so that we can move further. Basically the stack pointer is basically incremented. First I am showing it first the stat pointer value is at the bottom, which is shown as the 4001. Then as the element is going to as we insert the first element in the 4000 place, then the stat pointer value is 4000. After that, when we insert the second element at the 3999 place, then the stat pointer value point to the 3999 place. So basically stat pointer value is basically in the address point of view, it is decreasing because our actually this address is starting at 4001 and we are decreasing the value of the addresses. So basically the stat pointer is at this position 4001, then as first element is inserted, then its value is 4000. As the second element is inserted, its value is 3999 and so on. So basically the stat pointer indicates the address value, the present address value in of the stack, right? So moving to the next slide. Now you understand, Aditi? Okay. So moving to the next slide. So basically we assume that the items in the stack communicate with a data register DR, or you can say the address register. A new item is inserted with the push operation as follows. Once we insert a new item by using the push operation, so these two operations are performed. When the element is the stat pointer is pointing to one element minus, as we already show in the previous diagram. First the value of stat pointer is 4001, and once we push an element in the stat, then its value is decremented by 1, then its value will be 4000 because an element is inserted into the stat, and the data register uh, is showing the memory of the stat pointer basically. So these two operations are performed when we push an item onto the stat. The stat pointer is decremented so that it points at the address of the next word. So a memory write operation inserts the word from the data register into the top of the stack. So now a new element is deleted with a pop operation as follows. So once we delete an element, then a pop operation is follow, and these two operations are performed. Now the stat pointer value is incremented by 1, and also the memory in the stat pointer is stored in the data register. So these two operations are performed with the pop operation, and the above two operations are performed when using the push operation. So you just remember these two operations because in this example we are using the stat which is decrease in value from 4001 to 3000. So we are using the decrease in value, but once we are using the increase in stat values, which then the values are different. So by on using this example, you can remember the pop operations. These are the two operations for pop, and these are the two operations which are performed by using the push operation. So moving to the next slide. So these such type of operation we already discussed in the instruction set format. So the top element is read from the stat into the data register. The stat pointer is then incremented to point at the next item in the stat. So these are the working of the stat with the use of a stat pointer. So most computers do not provide hardware to check for stat overflow when the stat is full, or underflow when the stat is empty. So as most computers do not provide the hardware, so the programmer can check it manually, whether the stack is full or the stack is empty. So the stack limits can be checked by using two processor registers, one to hold. So the stack limit can be checked by using two processor registers, one to hold upper limit, which is 3000 in this case, and other to hold the lower limit, which is 4001 in this case. So two registers are there which shows the stack limits. So after a push operation, stack pointer is compared with the upper limit register, and after the pop operation, stack pointer is compared with the lower limit registers. So these are the uh, by using these methods we can check either the stack is overflow, that is the stack is full, or the stack is underflow, that is the stack is empty or not. So these are the two operations, or these are the two methods by which you can check the stack is full or the stack is empty or not. So all of you understand it? Just write in the chat box. Okay. So moving to the next slide. So the two micro operations needed for either the push or pop are an access to memory through stack pointer and updating the stack pointer. So these are the two micro operations which need to be performed by you or by the microprocessor of the CPU. One is an access to memory through stack pointer, and the next is updating the stack pointer. Either you can update the stack pointer with incrementing one value or decrementing the one value. So which of the two micro operations is done first, and whether SP is updating by incrementing or decrementing depends on the organization of the stack. Just as we discussed in the figure, it depends on the organization of the stack. As in our example, the stack is basically the decreasing stack, because in that stack the first value is 4001 and we are decrementing it to 3000, but the stack can be uh, start from the 3000 and it can move to the 4001. So in that case your values will be different. So in the figure, the stack grows by decreasing the memory addresses. The stack may be constructed to grow by increasing the memory addresses. If 3000 is your starting address and 4001 is the your last address, then that type of a stack is known as the increasing stack. In such a case, SP is incremented for the push operation and decremented for the pop operation. So just the reverse case, what we discussed in our figure, will be happened if the values of the stack is of increasing stack type. A stack may be constructed so that stack pointer points at the next empty location above the top of the stack. So these are just the explanation of the stack memory. So moving to the next slide. So in this case, the sequence of micro operations must be interchanged. A stack pointer is loaded with the initial value. This initial value must be the bottom address of an assigned stack in memory. Henceforth, stack pointer is automatically decremented or incremented with every push or pop operation. It is just the explanation which is given in words. So advantage of a memory stack is that the CPU can refer to it without having to specify an address, because the CPU knows that a stat is moving linearly, and the items are inserted or deleted in a linear fashion in one by one manner. Since the address is always available and automatically updated in the stat pointer. So basically stat pointer is used in order to basically push or pop an item from the stack in a linear fashion. So these are the advantage of a step. So more advantage of a step will be discussed in the next slide. So these are the important applications of a step. So first is efficient computation of complex arithmetic expressions. So complex arithmetic expressions are basically computed with the use of stat. Uh, as we need, as an example, if we need to calculate 5 plus 6 into 7, then it can also be calculated with the use of stat, basically, because we need to insert the operators in the stat. Suppose 5 is the first operand, so we take it 5, then 6 is there, sorry, then plus is there, so we need to insert the operators into the stack. So first we push the plus sign into the stack, then we are scanning, as we are scanning from left to right, then we got 6, then the other operator is into, and then we need to insert or push it onto the stack. As we know that the into operator is having the higher priority than the plus, so it can insert above above the plus operator. But if it is of lower priority, then we need to first pop the plus sign, and after that we need to calculate it. After that we get the 7, then we write it 7, and in order, after that we need to pop these operators. So first, according to the LIFO property, first the operator into pop out from the stack, so this, and after that the plus is popped out from the stack. So we need to calculate it, it is in this form. First 6 into 7 is calculated, which is 42, and after that we have two operands are there. One is 5 and the second is 42. So for after that plus sign will be evaluated. So 42 plus 5, so answer is 47. So that's how the by using this step, that the arithmetic expressions calculation will be very easy. And the second advantage is execution of instructions is fast, because operand data are stored in consecutive memory locations. As the operands are stored in consecutive means in the consecutive memory location, means it can be stored in plus one memory address in case of push operation, and in case of pop operation it can be stored in the minus one memory location. So that's why the operation or the execution of instructions is fast here, because all the operands are in stored in the consecutive memory locations. The third advantage is length of instruction is short, as they do not have address fields, as basically these addresses are basically are stored in the consecutive memory location. So the length of instruction is very short here. So basically, these are the advantages of stat-based CPU organization. And there is also one disadvantage of using stat. So the size of the program increases. So this is the major disadvantage of using stat. Uh, an important note is there: stat-based CPU organization uses zero address instruction. Uh, you can also refer this in the instruction set format. slides, uh, when we discuss the one address, two address, three address, and zero address instruction format, then we already discussed that stack is used in the case of zero address instruction formats. So these are the applications of a stack, and these are basically more advantages are there in using the stack, and there is few disadvantage of using the stack. So all of you understand it? Just write in the chat box so that we can move further. Okay. So moving to the next slide. Now the next data structure, which is also very important, queues, but from computer architecture point of view, stack is more important than queue. But basically, queue is also there in your syllabus, so we also need to discuss it in detail. So a queue is a linear data structure which follows a particular order in which the operations are performed. So the order is FIFO. So basically, queue works on the principle of FIFO, means first in, first out. Uh, it can be compared. A good example of queue is any queue of a consumer for a resource where the consumer that came first is served first. As you remember the queue in the railway platforms, or the queue in paying the electricity bill. So whoever come first will get the chance first. So basically it is in it follows the principle of first in, first out. So you can see from the figure here a queue is here, and you can see that here there are 5 items in the queue. So basically, this is the rear end, and this is the front end. So you need to remember it. A queue is having two ends. First is a rear end, and the second is the front end. So basically, if an item or if a consumer wants to enter in the queue, so it basically enters from the rear end. It basically enters from here, and it it is moving forward. So as more and more consumers or items are inserted in the queue, so the first item is moving to the moving forward, and it becomes at this position, it becomes at this point one, at point number 1. So but as the he proceeds uh, his task, then then it deletes from the queue from the front end. So there are basically two ends, or you can say there are two doors. In the from the first door you need to enter it, and from the second door you need to exit. So from the rear end you can enter, and from the front end you can exit from the queue. So these are very important, because in the stack there is only one position which is known as the top of the stack. But in the queue there are two positions. One is the entry point and the other is the exit point. So the entry point is known as the rear end, and the exit point is known as the front end. So basically, as in the stack there are two operations. One is the push and the pop. In the same way, the queue is having two operations. One is the rear end and the second is the front end. I think all of you understand it. So moving to the next slide. So a queue is a linear data structure in which elements can be inserted only from one end, only from the one end of the list. You need to note it, only from the one end, called the rear end, and the elements can be deleted only from the other end, which is called the front end, as we already discussed in the last slide. The queue data structure follows the FIFO, first in first out principle. That is, the element inserted at first in the list is the element which to be removed from the list. The insertion of an element in the queue is called the enqueue operation. The deletion of an element is called the DEQUE operation. As we already discussed in the last slide, you can see here that the NQ and the DQ is there. So this operation of insertion is called the NQ operation, and the operation of deletion from the queue is known as the DQ operation. So in queue, we always maintain two pointers. One pointing to the element which was inserted at the first and is still present in the list with the front pointer, and the second pointer pointing to the element inserted at the last with the rear pointer. So basically, uh, in performing or in programming the queue algorithms, we need to maintain the two pointers. First is the front pointer and the second is the rear pointer. So from the rear pointer we need to insert, or we need to uh, when the element is inserted, so rear pointer will be incremented, and when the element is deleted, then the front pointer is incremented. So these are the two pointers when we program the queue. All of you understand it? Okay. So now the applications of queue. So queue is used when things don't have to be processed immediately, but have to be processed in, first out order, like breadth first search. So this property of queue makes it also useful in following kinds of scenarios. So in these scenarios, the this property of first in first out will be useful. So when a resource is shared among multiple consumers, for example, including CPU scheduling, disk scheduling, or in the case of sharing a printer, then whichever or whoever gives the command of printing first will get its print command first, and following the first in first out principle. So when, and the second is when data is transferred asynchronously, that is data not necessarily received at the same rate as sent, so between two processes. Examples include input output buffer, pipes, file input output, etc. So in these type of applications, the queue is much predominantly used. So these are the applications in which queues are mostly used. So now the next topic is types of queues. So what we discussed is linear queue, and there are some specific types of queues which are also very important. So first is the circular queue, second is the priority queue, and third is the doubly ended queue, which is also known as the DQ. So let us discuss these queues one by one. So we can discuss the circular queue first. So as the name suggests, the circular queue. So you can see in the diagram here the queue is of circular nature. So the circular queue is a linear data structure in which the operations are performed based on FIFO, because as it is queue, so it follows the FIFO principle, and the last operation is connected back to the first position to make a circle. So it is also called a ring buffer. Basically, there is one problem in the linear queue. In order to overcome that problem, we need to use the circular queue. So basically, as you can see in the circular queue, this is showing the front pointer, and this is showing the rear pointer. So as you insert it, because the element is inserted from the rear pointer. So as you insert it, and there are 8 positions are there from 0 to 7. So once you insert all the 8 positions, then the queue becomes full. And after that, if suppose you have a list of 9 or 10 items, and as you insert each item in each position, so after 8 position the queue becomes full. Then if you want to insert your ninth item, as the queue is full, then it's a problem is there. So in case of linear queue there is problem, because in the linear queue, as there are, suppose 8 blocks are there, and you from 0 to 7, and if you insert each one there, and even though 4 or 5 items are deleted from the front end, so suppose there are 5 items deleted from the front end, so basically there are 3 items are there. So even though the 5 items are empty from the front, even though you cannot insert in the linear queue, so in order to overcome that problem, you can we develop the circular queue. So in this case, as all the items are filled, suppose all 8 items are filled, so and suppose 5 items are deleted from the front end. So so we can also insert the next items because the queue is circular. So basically, the circular queue overcomes the problem which is faced in the linear queue. So I think all of you understand it. So these are the, so basically in the next slide, this is abbreviated in the words. So in a normal queue, we can insert elements until queue becomes full. But once queue becomes full, we cannot insert the next element even if there is a space in front of the queue. So this is the problem with the linear queue. But by using circular queue, we overcome this problem. Then there are some other advantages of circular queue. It takes up less space than the linear queue. A new item can be inserted in the location from where a previous item is deleted. This is the second advantage. An infinite number of elements can be added continuously, but deletion must be used. So basically, the infinite number of elements can be added continuously. This is the most important advantage of the circular queue, which the linear queue does not have. So that's why we are much more using the circular queue concept. All of you understand it? Just write in the chat box so that we can move further. Okay. So next is the priority queue. So a priority queue is an abstract data type similar to a regular queue or the linear queue or stacked data structure, in which each element additionally has a priority associated with it. So basically, the in priority queue, each element is having a priority associated with it. So in a priority queue, an element with high priority is served before an element with low priority. So this is the concept of priority queue. All the elements are given priority according to their need or according to their value. Each element is given priority. So an element with high priority is served before an element of lower priority in the case of priority queue. So you can see this by using the diagram. So here you can see there are elements inserted in the queue 1, 2, 4, 5, 8, 9. So these are the elements inserted. So here we are using decrease in priority order. We are using this. So it means the element having the highest value is having the highest priority. So as we are using decrease in priority order, so the element with the top priority. So in all these elements, so 9 is having the highest value. So 9 is given the highest priority. So basically, the priority queue is based on the priorities. So there are basically two types of priority queues. So first is the ascending priority queue, and the second is the descending priority queue. So the example we discussed in the previous slide is basically of descending priority queue, as the values are decreasing there. So basically, in the ascending priority queue, removal of minimum priority element. So in the ascending priority queue, the minimum element is removed first, because the minimum value is having the highest priority. So remove top. So remove element with minimum priority. In the case of descending priority queue, so removal of maximum priority element. So the remove top, here remove element with maximum priority. So the use of priority queue is basically to assign the priorities to every element. And there are basically two methods. One is the ascending priority, in which the minimum priority element is removed first, and the second is the descending priority, in which the maximum priority element is removed first. So this is the priority queue, and these are its types. So all of you understand it? Just write in the chat box so that we can move further. Okay. So moving to the next slide. So the last type of queue is DQ, which is also known as the doubly ended queue. So is an ordered collection of items similar to queue. So basically, as the name suggests, doubly ended queue. So it has two ends. So it has two ends. Two ends, a front and a rear, and the elements remain positioned in the collection. So this hybrid linear structure, so basically it is a hybrid structure of a queue and a stack basically. So this hybrid linear structure provides all the capabilities of stack and queues in a single data structure. So basically DQ or W-ended queue is a hybrid structure of stack and queues. So moving to the next slide. So basically, there are two types of DQs. So first is the input restricted DQ, and the second is the output restricted DQ. So in the input restricted DQ, elements can be inserted only at one end, because it is input restricted. So this is, you can see from the diagram, this is the queue, and as the queue is having two ends, one is rear and the second is the front end. So every queue is having two ends, but in the case of input restricted DQ, so you can insert the value only from the one end, but you can remove the value from both the ends. So in the input restricted DQ, elements can be inserted only at one end, but elements can be removed from both the ends. As it is called input restricted, so input is restricted from one end. In the second type of DQ is output restricted DQ. So elements can be removed only at one end, but elements can be inserted from both the ends. So this is the type of these are the types of DQ. It is input restricted DQ and the output restricted DQ. So all of you understand it? So these are the three main types of queues: circular queue, priority queue, and DQ, which is doubly-ended queue. So moving to the next slide. So the comparison between queues and stacks. So all of you see this slide clearly? Just write in the chat box, or can I enlarge this slide? So only 5 minutes are there, so we only need to complete this slide in this 5 minutes. Okay. So the comparison between stats and queues. So basically, the first point is stats are based on LIFO principle. That is, the element inserted at the last is the first element to come out of the list, whereas the queue are based on the FIFO principle. that is the element inserted at first is the first element to come out of the list. These are basically the definition of stack and queues. Then the second point is insertion and deletion in stack takes place from one end of the list toward the top of the stack, whereas in the queues the insertion takes place at the rear of the list, whereas the deletion takes place from the front of the list. As we already discussed, there are two pointers. One is the rear pointer and the second is the front pointer in the case of queues. So in the case of stack, insert operation is called the push operation. In the case of queue, the insert operation is called the enqueue operation. In the case of next point, in the case of stat, the delete operation is called the pop operation, whereas in the case of queue, the delete operation is called the DEQUE operation. So in the case, the next point is in the case of a stat, in stats we maintain only one pointer to access the list called the top, which always point to the last element present in the list. Whereas in queue we maintain two pointers. This is very important. We maintain two pointers to access the list. The front pointer always point to the first element inserted in the list and is still present, and the rear pointer always point to the last element inserted element. So we in the queues we have two pointers. So the last point is stat is used in solving problems, work on recursion. Whereas in the case of queues is used in solving problems having sequential processing. So these are the important points of difference between queues and stats. So all of you understand it? So that's it for today's class, and there is one topic left. As there are only 2 minutes left, so we will going to discuss the last topic in the next class. So thank you very much. So now you can leave this meeting.